Yeah, me too.
So tomorrow is your part 2 of your multiple choice test. We've worked through pages 9 and most of 9 and page 12. Yesterday, I really want to focus on area volume. We did that. This morning, I did the morning review, page 19 through 22. I recorded it and it's on my website under today's date, so let me know if you have any trouble finding it. But no help session tomorrow morning because I got to do EOC prep. And then, well, we should be able to get through the rest of the pages that we didn't get to yesterday. So. Okay, so I think what we didn't get to was number 3 on page 9. So let's try that problem. Okay, it's asking us to find the limits of that expression. So it looks a little strange with this notation, but we know the first thing for any limit problem is just do what? Plug in, right? Let's just plug in and see what we're working with. Okay, so h is approaching 0. Let's replace all the h's with 0. Okay, you guys notice anything here? Say it again? What's that end up mean? Okay. A little bit more specific. 0 over 0. Okay, so you see a 0 in the denominator here. Now this is all in the numerator. So if I want to split it up, I could do this. Right, if I merge it into one fraction. Now, what is this portion equal to? Okay, it looks difficult, right? It looks like, oh, I got to deal with all this integral notation here. But is there something about the numerator that we can quickly look at and know what it's equal to? The bounds. Okay, so the bounds are the same. What does that tell us? Always 0, right? If my bounds are the same, my integral is always 0. So we know that this is giving us a 0 over 0. And if we have 0 over 0, what special thing can we do there? We can apply what? L'Hopital's rule, right? If you're dealing with a limit of an expression, and if it gives you a 0 over 0, you know there's a hole in the graph. We can do L'Hopital's rule. So let me rewrite this problem in the numerator and denominator. Makes it maybe a little bit easier to see. Okay, so we need to find the derivative of the numerator and the derivative of the denominator. I'm just showing the notation that I'm about to take the derivative of the numerator and denominator. Now the denominator feels a little bit easier here. What's the derivative of h? Is 1, okay? Now the derivative of the numerator, does that remind you of anything that we can apply with all this messiness here? So notice that we have an expression we got the integral that's impacting the expression. We also have the derivative that's impacting the integral, which is impacting the expression. So what do we know about these two? They're going to do what? So yeah, so which theorem are we using? Second theorem, right? We know second theorem, these are going to essentially cancel each other out. The upper bound is going to get inserted into the expression, and then we're going to multiply by the upper bound's derivative, right? So we don't have to do a whole lot of calculus here. We just have to kind of step through second theorem, right? So second theorem says if I'm pairing derivative and integral on top of an expression, the upper bound gets inserted into the expression and multiplied by the upper bound's derivative. I know this looks like chain rule, but it's not really chain rule. This is really a shortcut to these two processes undoing each other on top, impacting that expression. Okay, so the upper bound gets inserted into the expression. Multiplied by the upper bound's derivative, which is 0 plus 1, which is 1. And now that we have a different version of the expression, we can reevaluate the limit. So 0, insert the 0 into the expression. We get h gets replaced with 0. We get root 4 over 1, which is 2. Okay, I think we went through every problem on page 9. Let's go to page 10. Okay, the graph is a differentiable function. H is the integral from 0 to x of f of t dt, which of the following is true. So we're asked to compare between h of 6, h prime of 6, and h double prime of 6. Let's go ahead and build all the derivatives, and that way we can see all of them in front of me here. So here's h of x, I already have that defined. Let's find h prime of x. So if I want to find h prime of x, that means I need to find the derivative of that integral. Again, this is applying second theorem. We know these cancel out. The upper bound gets inserted into the expression. So we know h prime is really just f of x, right? So basically, we're looking at the derivative graph for h. Okay. So let's keep going. We know we can also build h double prime in terms of f. H double prime, if h prime is f, then h double prime is equal to what? So we drop one derivative down from h prime to h double prime, and f will turn into what? F prime, yeah. So let's compare all the values between h of 6, h prime of 6, and h double prime of 6. Okay, so let's do h of 6 first. H of 6, it's just looking at following what the rule says, integral from 0 to 6 of f of t dt. So 0 to 6 is the area or the depth integral here. Now, this is below the x-axis, and we may not know the exact area, but it's below the x-axis. So what is that going to get us back in return? Positive or negative number? Negative. It's accumulation of these negative y values. Now, if I just want to do a quick estimation, I can say that, well, it looks like it's, maybe a little bit smaller or larger than this rectangle. So if I did 5 times 4 as 20, I could just kind of estimate, okay, maybe that's around negative 20. All right. I know that it's not accurate, but it gives me some, or somewhere between 15 and negative 15 and negative 20, right? I know it's going to be somewhere in that range. Okay. So let's find h prime of 6. We know h prime of 6 is f of 6. What's f of 6 equal to? 0, yeah. So we have that. Let's find h double prime of 6, which is f prime of 6. What's the slope? What's f prime of 6? Yeah, somewhere, you know, it's positive, right? Maybe 1, maybe 2, but yeah, I guess good guess, 1. So now that we have all these values, we can compare them, right? Negative 20 is the smallest, followed by 0, followed by 1. 1's the largest. Okay, let f be the function defined by f of x, which is defined as the definite integral from 0 to x of 2t cubed. So right now, f of x is staying at a level above that 2t cubed minus 15 squared plus 36t. On which of the following intervals is the graph of f of x concave down? So anything dealing with concavity, we have to work our way down to which derivative? First, yeah, right. First derivative is for your increase, decrease, relative max, relative min. Concavity, concave up, concave down, point of inflection, that's all second derivative. So let's make our way down to the second derivative. So f of x is sitting at this integral level. So if I want to find f prime would be the derivative of this mess. So what's the derivative of the integral of this expression? What's going to happen here? Well, it's not just this, right? If it was just this, then yeah, it'd be 6t squared minus 30t, but it's the derivative of the integral of this expression. What's going to happen with these two operations? Cancel each other out, and then I just need to plug in the x, right? So really, it's just 2x cubed minus 15x squared plus 36x. Okay, does that make sense? So what we need to understand is that f is sitting at a level above this 2t cubed. So when we take the derivative, it's going to come down to this 2x cubed level. Yeah. The t goes away because it's second theorem. So second theorem, the upper bound gets inserted into the expression and then it just disappears. Technically, we also multiply by the upper bound's derivative, but the derivative of x is just 1, so we can just ignore that portion. So this expression is really just the first derivative level. So now if I want to find f double prime, I can now go through power rule now that the integral has been taken care of. Okay, so now this becomes 6x squared minus 30x plus 36. So now we can go through and find our critical points, create our second derivative sign line. Okay. Okay, I can set equal to 0. I can take out a GCF. Continue factoring, multiplies to be 6, adds it to be -5. Make my second derivative sign line. Test my intervals. I can test 1, I can test 2.5, and I can test 4. Okay. And I like to insert into the factored form of my expression. So if I insert 1 in for x, 1 minus 2 is negative, 1 minus 3 is negative, 2 negatives makes a positive. So concave up. 2.5 minus 2 is positive. 2.5 minus 3 is negative. Positive and negative is negative. Concave down. Plug in 4. 4 minus 2 is positive. 4 minus 3 is positive. Concave up. So the intervals of concave down is just what's between 2 and 3. Okay, so really, I just want us to really practice with second theorem and just not get thrown off by second theorem and just understand that it's a shortcut way of working with messy functions that have the integral notation in front of it. Okay, number 7, again, is asking for the derivative of an integral of an expression. So second theorem also applies. Okay, we know these two operations undo each other. I'm going to just plug in my upper bound into the variable and then multiply by the upper bound's derivative. Yeah. For number 7? Yeah, so here's the rule that we're applying. So second theorem says if I'm pairing these two operations on top of one another, what's going to happen is my function is going to change. It's not going to change much. The upper bound is going to get inserted into the expression. So f of p of x multiplied by the upper bound's derivative. So same thing here. My upper bound is 2x. I insert 2x into the variable of my expression, which is here. And then I multiply it by my upper bound's derivative. 2x becomes 2. Okay, number 8. F of x is 2 sine of e to the t over 2. G is the antiderivative of f. So we really want to create some sort of a notation so we can kind of really see that relationship. We know g of -1 is -2, find g of 3. So it says that g is the antiderivative of f. Which means that f is really what in terms of g? F is really just g prime, right? Because if it takes the integral to make f equal to g, that means that f is really at the g prime level in order for that to happen, right? And also you can take the derivative of both sides and see that g prime is equal to f of x. Okay, so this is an important relationship that we want to make sure we understand. And if I have the derivative and I have a starting point and I'm trying to find a final position, I like to use my formula, final position equals initial plus displacement. So I'm looking for g of 3. I have g of -1. I want to find the change in position between -1 and 3. I can just insert g prime, and g prime is my f. So that's my displacement. So g of -1 is my starting location. The integral from -1 to 3 will give me how much I've progressed from that starting point. And then if I add those together, I can figure out where I end up at 3 seconds or whatever that variable, that value is. So I can just enter this into the calculator. The depth integral from -1 to 3 is displacement. So that means I'm starting at -2, but then I move 4 units and change, add those together. I'm going to be at location 2.255. Okay, last page, page 11, but we've already done 12, so page 11. Okay, f is a continuous function, f prime equals f of x, then the integral from 1 to 4 of f of root x over root x dx equals. So it looks messy, and we know that we don't have a rule that can handle this interval. Also, we know that lowercase f is going to rise up to uppercase f, but there's a root x inside that function notation. So it's messy, but how do we deal with messy integral problems? What's the method that we use to clean that up to make it easier to work with? What's that method that we use? Yeah, U substitution, right? U substitution. The whole purpose of U substitution is to take an integral problem that is hard to work with and try to make it easier and cleaner with a rule that we use. Okay, so let's identify. Yeah, let me put this on a separate sheet. Maybe that'd be easier to see the steps. Yeah, let me do that on a separate sheet. Okay, so we know our U value is targeting that root x, and we're trying to replace that dx, and we're hoping that after we go through this U substitution, we do need that root x to go away, right? We can't do this, we can't find an integral rule unless that root x is dealt with, and we're hoping that that root x will take care of it. So let's go through our steps here. U equals root x. You know root x, same thing as x to the 1/2. Okay, du dx, 1/2 x to the negative 1/2. Do some cleanup here. I'm going to bring it back in terms of root x just so that I can make the match a little bit easier for me to see. Cross multiply, dx equals to root x du. All right, make my substitutions. So we want things to clean up, and we do see that root x go away. And that is the important thing, right? The variable has to go away. It's okay to have a leftover coefficient. So that 2 we can drag out in front. Okay, I'm purposely leaving out the bounds because I know I got to deal with it, so I'll deal with it later. So this is clean, right? It's a lot easier to interpret what we do with this step rather than at the beginning, right? Because at the beginning, it just feels like a mess. So the whole point of U substitution is after U substitution, you should be staring at a much easier problem to work with. Okay, so what happens with lowercase f of U? What's the antiderivative of lowercase f? Turns into what? Uppercase f, right? Because it tells us that f prime is f of x, so we know the antiderivative of f prime is going to make it rise up to uppercase f. So lowercase f becomes uppercase f. This is my antiderivative. Let's bring back the original variable. And now I can work in the bounds, right? Now that I have my antiderivative, my original variable, I can use the 1 and the 4. So root 4 is same thing as 2. So I have 2 uppercase f of 2 minus 2 uppercase f of 1. Now, if we had a function f of x that we could pull values from, we would do that. But in this case, we only need to go as far as the multiple choice asks us to go. So 2f of 2 minus 2f of 1 is enough for us to match with the answer choice. So answer choice A. Okay. Next step, number 10. Right, particle moves along the y-axis. So that means this particle is just moving up and down on the y-axis. Up is positive, down is negative. Its velocity is given by v of t. The position of the particle as 4 at time t equals 0. What is the position of the particle when its velocity is first equal to 0? So we have to first set velocity equal to 0 because we need to find the upper bound, right? We know the lower bound is 0, and we need to figure out the upper bound. So we're going to set v of t equal to 0. Now, this is not something that we can, or that we would want to solve by hand. Right? So this is really calculator question. So what we want to do is really, if we just graph this function, we can just look to see where the graph intersects with or across the x-axis, and that is our x-intercept. That's our solution here. So try that here. So I'll go to y equals. I'll do zoom 6. I'm looking at going to look for some x-intercept that's after 0, right? And I know it's a mess here, but really the first intersection that I see after 0 is going to be between 1 and 2. So I'm going to just do zoom box here so I can just zoom in on just that portion that I want to look at a little bit more closely. I'm looking for the first occurrence of a 0, and that's going to be right there. So I'm going to do second trace, choose a second trace 0, and I'll choose the cursor point to the left of my x-intercept. I'll choose a cursor point to the right of my x-intercept. Hit enter twice to get to this point. So it's guess question mark. I'll hit enter a third time. 1.379. Okay, so p equals 1.379. Okay. So I'm looking for my final position. I have my initial position, and then I can do my displacement using velocity. So I know that x of b is equal to x of a plus the integral from a to b of v of t. Okay. If I know where I started, and if I know how much distance I'm going to, how much movement I'm going to accumulate, I can add those together to figure out my final location. So I want to find out what is my location at 1.379. I know I'm starting at 0, so I go from 0 to 1.379, make the calculator do the work here to get my displacement. So x of 0 is 4. So I'm starting at location at y-intercept 4, and then I'm going to go down 1.533 units. So then that means at 1.379 seconds, I'm going to end up at y on my y-axis at location 2.466. Now, this particle motion formula can also be adapted for velocity and acceleration. Right? I just move everything down one derivative. I can say v of b. If I want to find my final velocity, I can do my initial velocity plus the displacement of my velocity. So I can do the same process for the problem below it. Number 11 is as a particle moves along the line, so that its acceleration is given by a of t. We know that the particle's velocity at 0 is 5. What's the velocity of the particle at 3? So I can just repeat the same formula as above, just adapted for velocity. So my final velocity equals initial velocity plus the displacement of my velocity, which is the integral of acceleration. Again, make the calculator do the work for us here, but the setup, we just using that particle motion to help us find the location. Okay, number 12, use substitution. So we're not asked to solve it all the way. We just need to solve it, get it to the point where it will match our answer choice. But they do give us a good starting point. We know the u value is root x, so we'll just go as far as the problem needs us to go. Okay, we see that the root x is not going anywhere, but we know that u equals root x. And if you look at your answer choices, looks like they're able to just represent everything in terms of u. So why don't we just make that substitution? We're not trying to solve it. We're just trying to do a series of substitutions so that we can make it match whatever form the problem is asking us to go with. Now, they also want us to put the bounds in place with this notation. Now here, everything is in terms of what? Which variable? U. But my bounds is in terms of what? X. So I have to convert it to be in terms of U so that I can match the answer choice here, right? So here I can't quite go, make this problem go to X, because if I do, I may be solving the problem, but it's not matching with the answer choice that they want. So so we're kind of forced to have to go through changing the bounds to be in terms of u. So that means our lower bound, if x is equal to 0 and our u is root x, we know that u is equal to square root of 0, which is 0. And if we know that if x is equal to 9 and u is equal to root x, then root 9 is equal to 3. So that will allow us to put 0 and 3. To make it match the answer choice that we're looking for. So the 2 gets pushed out in front, and then it's going to match answer choice A. Okay, running out of time here. 13 is just differential equation. We've done enough of that. Hopefully you guys can to work through that as extra practice. So, tomorrow, your test, which will be 8 questions over integral topic. Come and get your phone. Have a great day, guys. Study for your test for tomorrow.
Oh, man. This problem, I like was wondering. How do I start this problem?
So you see it looks like a messy integral problem, right? And if it's a messy integral problem, I'm always thinking, how can I make it cleaner? And I want to just go through U substitution. And my U value is going to be that root x inside that parentheses. And then my hope is
Okay.
that the root x in the denominator will go away when I take this substitution.
Gotcha. So, okay, I understand that. I don't understand like what this question is asking. So, is it just asking for a simpler version of the problem?
It's asking us to find the antiderivative in terms of uppercase F. Now, I know this looks messy, but this is gonna end up cleaning up to be something that looks a little bit cleaner. It's gonna end up being lowercase f. Okay, well, I mean, it is lowercase f. So the integral of lowercase f is gonna make it rise up to uppercase f. Because uppercase f is the antiderivative of lowercase f.
Gotcha.
So it's not power rule, but it's just the notation to indicate that I'm taking care of the antiderivative. And then from here, get it back in terms of x, plug in upper and lower bound, and I can make it match.
Okay. Okay. Last question. What is this? Oh, it's explaining the
Yeah,
uppercase F is
yeah.
okay.
So you really can write this as uppercase f prime of root x if you wanted to.
Gotcha. Okay, thank you.
Obviously,
Thank
let's
you.
finish the whole thing.
Okay, careful, thank you. Thank you.
Mom pulled me out into the hallway. It was like, my son can't get hours, all this stuff. How'd she go up to you? I don't know how she found me. Wait, what? I was like, that lady who pulled me out of the hallway was a mom.
That's so weird.
Oh, was NHS. I mean, like, she like found me. Like, she had my whole schedule printed out. She's like, I've been talking to Silverman. Miss Silverman, like, she said there's no possible way to make him to make it hours.
I thought she was someone with the school.
No, like, I don't, it was really weird. And I was like, I don't know. She was like, my son, like, he means so well. Like, he needs to work, like, y'all can work with him. And I was like, you need to go talk to Miss Silverman. She's like, I've already talked to Miss Silverman. Like, she said there's no possible way, so I'm coming to you. I was like, I was like, if Miss Silverman said no, then like, I was like, so I just told her to email me. I was like, just email me. Like, I was like, that is like stalkerish. That's scary. I was like,
Fair to put it on the student. That's.
I know, especially, and then she started like bad mouthing Miss Silverman to me. And she was like, I was just so shocked that she would do that to me. And I was like, I understand.
How is that allowed that they can just get your schedule?
I think she was like a substitute teacher or something.
Yeah, so makes sense.
Pick up.
Sorry for you guys going through that.
It was so awkward. I just didn't know what to do.
That's great.
If you want to be there.
Okay, I'll just take 5 minutes.
Also, we're thinking about things sort of.
What is that? Like sticks to me.
I have 7 or something.
We have no funny. So it's not doing all that. I think a Thursday after.
Yeah.
Friday afternoon.
That sounds good. We can do that.
Don't.
I'll just send a message to leaders. Usually that's.
Sounds good. It's 12. Yeah.
Okay. Yeah, you do.
Please, right, we hit that. Covering. Can't, what can their cover up to?
It's an 80.
80.
Well, you can do test correction, right? Okay.
Okay, you guys are both taking the same.
Yeah.
I mean, it's a nice spread out.
Yeah. Actually, on Irving. Thank you.